The next question is, how do we compute matrix Q? Now notice what we have now is a bunch of unitary matrices, such that if you multiply them times 8, you get this upper triangular matrix, or upper trapezoidal matrix, or whatever you want to call it. Alright, well remember that these are all householder transforms. Well, they're sort of kind of householder transformations because they may have these extra ones in the top left corner. But the fact is that the inverse of H3 is H3 itself. The inverse of H2 is H2 itself, and so forth. Okay? So, what we can do is we can rewrite this as A is equal to R times H3 times H2 times H1 times H0, where obviously if our matrix had more columns, we would have more such matrices. Okay. If we multiply all of these together, then we end up with a unitary matrix. And we end up with something that starts looking like a QR factorization. The only catch being that Q is now a square matrix, and R may have more rows than it has columns. So let's call that Q. And the question then becomes, how do we compute Q? Well, the way to think about this is that we can take our identity and multiply that by H3, and then by H2, and then by H1, and then by H0. As a matter of fact, if we take I not to be the identity, but the first n columns of the identity, then we start with something that looks like this for this example. Okay, so these are now the first 4 columns of the 5 by 5 identity matrix. Okay. Now, remember that this last unitary matrix really was the householder transform that only affected the last 2 rows. So if you go over here, if you apply the householder transform to this, you will only take linear combinations of these 2 rows, and as a result you will change only these 2 entries into non-zero entries. Okay, so what we're looking at right now is that. If we then go to the next one, that householder transform affects the last 3 rows. And notice that what that means is that after you apply it to what you just computed, these entries end up being non-zeros. And that way you can work your way back. And by working your way back and by carefully taking advantage of where the zeros exist in the identity, you can greatly reduce the amount of computation that you need to perform. As a matter of fact, if you think about it, the amount of computation that you need to perform going backwards like that is identical to the amount of computation you have to do going forward, modulo the computation of the householder transforms, or the householder vectors themselves. So what this then gives us, if we only work with as many columns here as we had columns in the original matrix, is actually the Q that you can then pair with this upper triangular matrix right here to get the same QR factorization that, say, the Gram-Schmidt orthogonalization process computed. Not quite. Why? Because when you use householder transforms, you may put a positive or a negative value on the diagonal, if we're working with real valued matrices, while the Gram-Schmidt process forced positive values to appear on the diagonal. But that's a minor